Okay, welcome everyone. It's my pleasure to welcome you all at this IAMP One World Mathematical Physics seminar. Today we have Michele Schiavina from ETH Zurich, and he's going to tell us about Ruelle Zeta function from field theory. And I just want to remind you that this lecture is being recorded and you can watch it later on our YouTube channel. But right now, Michele, the floor is yours. Please go ahead.
Thank you very much. Thanks for the opportunity to present this project to the One World seminar, to interesting set of interesting audience. And this project is a combination of several different approaches to, well, the mathematical physics, I would say. And it combines work within the world of dynamical systems with work within the world of field theory. And these are two areas that don't always interact. So it was spurred by, let's say, a throwaway comment of a colleague of mine during a seminar, and we started talking and we saw that maybe there was something in the work that he was doing and what I was doing that could come together into a perhaps better understanding. So the plan of today's talk is to describe what can be thought of as a field-theoretic interpretation of Ruelle Zeta function in the context of dynamical systems, and a reformulation in these terms of a conjecture of Fried. I will first tell you some historical basics about the Ruelle Zeta function and how it is seen as a tool to count geodesics, and how it features in a long-standing conjecture due to Fried that connects dynamical system, chaotic dynamical systems with the world of topology, algebraic topology, and manifold invariance. Then I will try to argue that it makes sense to think about these topics, looking at them from the angle of field theory. So in particular, I will discuss what is meant by gauge fixing in field theory, and in particular for a topological theory called BF. The upshot, so the take-home message, in case you want to switch off or lose track of it, is that I think what I will try to argue is that Fried's conjecture can be rephrased as a gauge fixing independence within the world of field theory for BF theory. Recent work has brought us to a unified approach to local constancy of several of the elements in this picture, which relates to the notion of gauge fixing invariance, so on families of gauge fixings. I will conclude this talk with some field-theoretic interpretation, some extensions in the direction of field theory of several objects that are of use in, well, we'll see. So this basically is a joint work with Charles Hadfield and Santosh Kandel, which you can find online and has been published. And more recent work stems from a master thesis of my student Thomas Stucker, who did a great work. And you can find it already online in case you're interested. This is before the publishable version comes out. So let us begin with some basics of what I will discuss later on. So today we consider an n-dimensional, compact, connected, and oriented Riemannian manifold without boundary, and we construct the unit sphere bundle from the cotangent bundle using the metric. Now on M, we have a naturally defined flow, the geodesic flow, that sends a vector to the tangent vector to the geodesic starting from V. And we denote the generating vector field of this geodesic flow by x of g. So whenever we have a structure like this, we can realize that we also have a contact structure on the manifold. If we denote by alpha the pullback of the canonical Ruelle form on the cotangent bundle, the triple mxg and alpha gives us a contact manifold with a choice of a Reeb vector field. For those of you who are unfamiliar with this notion, what this means is that we have a one form alpha and a vector field xg such that their contraction is 1, and the contraction with the derivative, the differential of alpha is 0. Alpha also gives rise to a volume form on the manifold. And this volume form is preserved by the geodesic vector field or the Reeb vector field. Now, in fact, what holds in general on a contact manifold is that if we denote by omega k0 the subspace of differential forms that are in the kernel of the contraction by the Reeb vector field, we have a splitting which is pretty much Hodge-like, and we'll come to that later, such as this one. Now, if the metric that we started from has negative sectional curvature, the geodesic flow has the property of being Anosov. Anosov flow is such that the tangent bundle to the manifold on which the flow is defined admits a flow invariant splitting into what are generally called neutral, stable, and unstable subbundles, such that the stable directions are contracting and the unstable direction are expanding, following this, this law. Now, this is can be taken as a prototypical example of a dynamical system with a chaotic behavior. So this is just for us to know that this is the type of setup that we're working on. In this setting, one can define a zeta function as I presented here, where the product runs over the set of primitive, I should have said, closed geodesics, so single winding orbits that have multiplicity 1, and denoting by L of gamma the length or the period of the geodesic, we have this product. Now, the Ruelle zeta function, you can think of it as a means to counting geodesic lengths, and one can draw the analogy with the Riemann zeta function as counting prime lengths or prime magnitude. This definition can be modified slightly, can be twisted by including a Hermitian vector bundle on top of our previous construction of a sphere bundle with a compatible flat connection, nabla, which gives rise to a representation, a unitary representation of pi1 of the manifold. In this case, you modified the definition of the zeta function as presented in red. And we typically talk about twisted Ruelle zeta function. In this case, I will probably forget to say twisted most of the time, but for the next, for the remainder of the talk, I will always think about this example. One can also be interested, and we will be interested in the case where the RAM cohomology vanishes with this twisting. So you see that we have a flat connection. Now you can enrich the RAM differential with this flat connection and obtain another coboundary operator, derivation that squares to 0, So there is a cohomology theory, and this is typically denoted by twisted Aram cohomology. So we will also assume that this twisted Aram cohomology vanishes. All of this can be generalized, but this already accounts for a large class of examples. Now, I will be very quick on this. There is a large number of works that discuss the properties of this zeta function, and that essentially ensure convergence in large enough real part of the parameter, and that ensures the meromorphic extension of this zeta function to the whole complex plane. Okay, so we will just assume that that has been taken care of, and we're working with a meromorphic function. So this is a probably incomplete list of people that worked on this. If well. So in the same geometric setting that I just presented to you, we can define another quantity, which is the analytic torsion of the manifold, given the twisting by the representation. So here we need to define a Laplacian. So we need a metric on the whole space. Now, in general,
may I ask a question?
Yes, of course.
Yes. So are we always assuming the Riemannian metric, not the Lorentzian metric?
Yes. Here I'm always Riemannian.
Okay.
So here you can define the analytic torsion given a Riemannian metric on M. And it is a classic result that the analytic torsion is actually equal to Reidemeister torsion, which is a topological invariant. So the essence is that, yes, to define this object, we need to choose a particular metric on the manifold, but we can then prove constancy on a family of metrics and equivalence with the Reidemeister torsion. So in this setup, then it makes sense to think that these two objects might be the same. This was conjectured by Fried in '95. So essentially, the conjecture tells us that the value of the Rosetta function at 0, the absolute value here, coincides with what computes the analytic torsion of the manifold. This has been originally proven for hyperbolic manifolds and was later extended to a number of other cases. Here again, there is a large literature on this, and there are ramifications of this statement. I just want to say that in general, this conjecture is pretty much open, another thing that I should say, this relates to recent work of Viet-Tang, Rivière-Guillemot, and Shen. One generalization of this is when you forego the working on sphere bundles and you just say, well, I have a manifold M with some annus of flow on it. And you can phrase the same conjecture for the annus of flow, for the zeta function associated to the annus of flow.
Sorry, Michele,
yes.
Can you remind me what was rho in the definition of the twisted Ruelle zeta function?
It's the representation induced by the flat connection. So you take the holonomy of the flat connection and this along a closed geodesic, and this gives you a representation of pi1.
Mm-hmm. Okay, thanks.
Okay. So what does all of this have to do with field theory is not clear at the moment. And so I will need a short digression to introduce the main elements of field theory that we're going to, that will be necessary. So for those of you who are experts here, I will certainly talk about a very specific, simple scenario. Okay, so first of all, we will restrict to the case in which fields are sections of some vector bundle. This can be generalized, but it will not be our case. And I also want to specialize to the case where I have a quadratic local functional over the space of sections of the vector bundle. And I write it in this form, where D denotes some differential operator. The idea of field theory, for those instead who are not familiar, is that we would like to make sense of sums over configurations, but typically we are not allowed to integrate in these functional spaces because of the lack of a sensible enough measure mu f0. So
may I ask a question again?
Yes.
If you're working in the Riemannian metric, then I think it's essentially Euclidean. Then I think in the partition function or the path integral, the I must be replaced by minus sign because it's essentially the weak rotation. That's what I think.
Well, I mean, yes, you can think of it like that, but here we want. I mean, you can also discuss the general scenario with I. I mean, that's not going to make much of a difference. But, yes. So okay, so the point here though is that we need to find a sensible definition for this partition function that doesn't involve integration essentially. So typically what this is, the standard approach here is to define this object via stationary phase formula, which is taken as a definition and not as a result. And this involves the regularized determinant of the operator that featured in the original action function. This clearly gives us a problem immediately whenever the theory admits local gauge symmetries because we have degenerate directions. So along the orbits of, let's say, if you're thinking about a gauge group or a gauge Lie algebra, you have certain degenerate directions, and you need to find some procedure to make it sense. Physically, what we're trying to do here is we're trying to count only inequivalent configurations along this equivalence relation given by gauge symmetry. And so we say that we need gauge fixing. Gauge fixing, you can think of it as the process of counting only configurations only once or a finite number of times. There are many ways in which you can implement gauge fixing. And one possibility that would be our choice is the Batalin-Vilkovisky framework, which is a chromalogical framework for field theory. I think that many of the things that I will say can be applied to other scenarios, but for me, this is largely more convenient, and we'll stick to that. So what is the Batalin-Vilkovisky formalism in a nutshell? So for us, a classical Batalin-Vilkovisky theory is the data of a four-tuple as written, where f omega is some graded -1 symplectic vector space, which we call the space of BV fields. Q is a degree 1 vector field, so a derivation of degree 1 of the algebra of functions, if you prefer, that squares to 0, which is often called the classical BV operator.
Excuse me, what does it mean, -1 symplectic?
Yes, so -1 symplectic means that if you have local coordinates or you denote fields in a certain, you look at fields, the fields are paired so that their degree is shifted by -1. So you're pairing fields of degree k with fields of degree -k-1. So here we are working in a graded setting, so a graded vector space, which means that our fields will have an assignment of a degree, integer number. S is a function of degree 0, which is often called a BV action. And it must satisfy the classical master equation, which is the statement that, well, equivalently, either the Q and S form a Hamiltonian pair, or the bracket of S with itself is 0. And this is a statement that is non-trivial because of the -1 pairing that I just mentioned. So as I said, F and S are extensions of the usual space of fields for standard field theory, where you add auxiliary fields in non-zero degree. The space of functions on this graded vector space comes equipped with a differential given by Q, and you have the structure of a complex. This complex tells us that cohomology in degree 0 is simply the space of gauge invariant functions on the critical locus of the original action. Okay, so this is just to understand what we're working with. In this,
excuse me. So there are two actions, S and S naught. Is it correct?
That is correct. So S naught is the original, let's say, degree 0 physical action, and S is some extension that involves also higher degree fields.
So is S quadratic as well? As naught was quadratic.
Yes, I will assume that S is also quadratic. It need not be, but in this case, I will assume it.
Thank
And
you.
is all the auxiliary fields called the ghosts?
I'm sorry?
And is the name for the auxiliary fields, are they called the ghost fields?
Yes, so ghost fields are often one denotes fields in degree 1 with the terminology ghost fields. Okay. So coming very briefly to the quantum setting, this is the ideal scenario that one would like to have, which works mostly in finite dimensions, so I will mention that. This data gives us an odd Poisson algebra. There are two algebras here, sorry. And this is additionally enriched into a so-called BV algebra if there exists a co-boundary operator delta called the BV Laplacian that generates the Poisson bracket in this sense. Once we have this operator, one can define the quantum master equation as the statement that the exponentiated action vanishes, is in the kernel of the operator. Okay, we will not need to worry too much about these details, as you will see, but it's just to give you a motivation for what will come. And in finite dimensions here, and here I should stress that this is really only a theorem when the space of fields is finite dimensional. Given a classical BV theory with additionally the data of a BV Laplacian and S solving this quantum master equation, we have that given any choice of Lagrangian submanifold in a smooth family, the value of this integral will be constant along this family. Okay, so this is a motivation for why we think of gauge fixing in the Batalin-Vilkovisky formalism as the choice of a Lagrangian submanifold inside this space. Okay, this is a motivation that comes from a finite dimensional theorem. All right.
Could you explain what Brezinian mu T is?
You should think of it as a density in the odd geometric sense, in the graded geometric sense. It's something that allows you to integrate over a space that might have even and odd coordinates.
Oh, I see. Thank you.
So let's look at a specific example. Let's look at the example of BF theory. Now, let's go back to the geometric setup that we had before. When phrased in the BV formalism, abelian BF theory is the following data. I take two copies of differential forms with values in the Hermitian bundle that I constructed before, and I shift them in degree in the following way, so that A, bold A, is an inhomogeneous differential form whose component of homogeneous degree K has total degree 1 minus K. Okay, this is what we mean by shifting it in degree like that. Similarly for B, this should be a bold B. Apologies for that. The symplectic form and the action functional are given by these two expressions, which are local expressions on the space of fields. Now, in what will follow, we consider various gauge fixing choices for BF theory. So motivated by the finite dimensional theorem that I told you before. These are Lagrangian submanifolds that all arise in this sense. So we specify a operator that we call a gauge fixing operator with the property that Q squares to 0 as well. And we will see that we will also have an adjoint map with the same property. And additionally, and this is the crucial point, there is a splitting of the whole space of BF fields into the image of Q gauge fixing on the two copies of differential forms and the image of Q perp. Lagrangian in this infinite dimensional setting means, for us, there are several notions, but the one that we prefer is isotropic with isotropic complement. So both L and K are isotropic and they are complementing each other. Now, again, if we choose a Riemannian metric on our manifold M, notice that to define BF theory, we didn't need any metric. We can define the gauge fixing operator given G as the codifferential for the twisted de Rham differential. And then we can compute the Lagrangian submanifold to be the image of the gauge fixing operator, two copies of it. And this is nothing but the Lorentz gauge that you probably have seen or heard of. Then there is an old result by Schwartz, which can be interpreted in this language as the statement that the partition function for BF theory, given this gauge fixing Lagrangian, is precisely the analytic torsion. So one perhaps heuristic way of looking at this is goes through by connecting the partition function to a gauge fixed form of the Laplacian defined by G. And this is because you can rewrite the gauge fixed BF action as this sum. So then you can think of the partition function here. There are some details that are I'm swiping under the rug, but essentially the upshot is that the partition function can be seen as a regularized superdeterminant of this operator. And this is precisely the analytic torsion. For later reference, notice that this operator that features here, d star d, is nothing but the commutator between the de Rham differential and the gauge fixing operator restricted to the gauge fixing Lagrange. Okay. Now let's again go back to the original setup and consider that on ME alpha and X, where now X is just the Rib vector field of alpha, so not necessarily a geodesic flow, a geodesic vector field. Remember that we had this splitting for any contact manifold. So then if BF theory is cast on a contact manifold, there exists another option for gauge fixing, which is given by the contraction with X. And the perp gauge fixing operator, this adjoint, is given by wedging with the contact form. So there is a different gauge fixing Lagrangian, which is almost a axial gauge, if you know the terminology, which is essentially, sorry, here there should be a +2, but it's essentially the image of iota x or the kernel. Now, in recent work with Hadfield and Kandel, we have shown that indeed one can interpret the partition function of BF theory with this gauge as the Lie derivative, the superdeterminant or the determinant of the Lie derivative operator, where we use a slightly different regularization scheme than zeta function regularization. So briefly on that, if we denote by LK the Lie derivative operator along the Rib vector field, whenever the Rib vector field also generates an Anosov flow, as we saw before, one can make sense of the so-called flat determinant of this operator. This is essentially a version of the standard regularization, but there are two important elements. One is that the trace is not the usual trace, and the second element is that we're using two regularizing parameters. One is S and one is lambda. The flat trace in this case is computed by Guillemin flat trace formula, which yields a distribution on R+, which is given here. Now, the details will not be important, but I put them here so that you get the feeling that this is very concrete. And using this, we have shown that, in fact, the superdeterminant and hence the partition function of BF theory in this gauge fixing choice is precisely the Ruelle zeta function at lambda here. So you get the result by setting lambda to 0. Sorry, I have anticipated myself. So if you cast BF theory on a contact manifold whose Rib vector field is Anosov, allows you to rephrase Fried conjecture as the statement that the same theory yields equivalent results when two different gauge fixing choices are chosen. Now, again, if this were a finite dimensional problem, then the BV theorem would tell us that the only thing we need is a statement, a homotopy, a Lagrangian homotopy between L of G and L of X. So a smooth family of Lagrangian submanifold that connect one gauge fixing choice with another gauge fixing choice. In an infinite dimensional setting such as this one, though, we don't automatically have a well-defined BV Laplacian or a generalization of the BV theorem that is applicable immediately, at least. So this led us to find a local constancy statement for at least partition functions of this type, so that we could show that partition function indeed should be constant along some smooth family of gauge fixing choices. And as I mentioned already, the analytic torsion we know is locally constant. So seen as a partition function for BF theory, given a choice of metric, we already know that this is locally constant thanks to Ray and Singer original proof. And recently, we have a similar statement for the Ruelle Zeta function thanks to these guys that really did a great job. And so, yeah, we do know already that both the analytic torsion and the Ruelle Zeta function are locally constant in the appropriate sense on smooth family of choices of the various data that are needed to define them. But what we wanted to do here is to use field theory to produce a unified statement that encompasses both scenarios, so that we can perhaps later find a link between the two. How much time do I have left? Just to
yeah, so it's usually about an hour, so you have about 25 minutes at this point.
Yes, I think I will. I should be able to do it. Are there any questions so far? Maybe I can. Okay. So how do we set up this statement of gauge fixing invariance in BF theory? So we want to consider a family of gauge fixing operators, such as the ones that I presented for you before. So I will parameterize these operators by parameter tau. I want that for every tau, for each tau, there is a splitting of the space of fields. In particular, I'm going to look for something finer. So I'm going to look for a splitting of differential forms with the property that this splitting is preserved by the operator that I obtain bracketing the de Rham differential with the gauge fixing operator at time t. Additionally, I want to assume that this so obtained differential operator also has some technical properties which will all be satisfied for the cases that we're interested in. For example, it generates a semigroup. Additionally, I want to restrict the type of families that I'm allowed to look at. And I will look at families generated by bundle automorphisms, such as this one. So I have a beta of tau, and I obtain the gauge fixing operator at parameter tau by adjunction with beta. This will yield a Lagrangian homotopy given by well, the images of the gauge fixing operator at time tau, 2 copies of them. Furthermore, we need some technical assumptions, which, as I will argue later, are satisfied for the cases that we're interested in. But for those of you who are interested, these are essentially certain microanalytical properties of the Schwartz kernel of the semigroup of operators. We also need a certain good behavior of the distribution obtained by tracing this combination. And we need also some analytic continuation in S and lambda of this function here. Okay, so for those of you who are not interested, you should bear in mind that yes, this statement will not be is not so general, but it has well-defined boundaries that we can explore and perhaps one day eliminate. With this setup, we have that given such a family of gauge fixing operators, which are related by automorphisms, and with d of tau being the bracket of, sorry, here Q should be the nabla. This is a typo, apologize. Given a splitting that is d tau invariant, and assuming that the flat determinant is well defined and non-zero for all tau, given the analytic requirements that I just showed you before, then the super determinant of this combination is constant in tau. So essentially, the superdeterminant here of this combination will be taken to be the partition function of our theory, given this gauge fixing. But
excuse me,
yes.
What is tau?
Tau is just a parameter between, I don't know, -1 and 1.
Yeah, so
or 0 and 1.
So you have a smooth family of gauge fixing operators depending on tau. That's
correct.
Okay, thank you.
Okay, so let's try to apply this setup to the scenarios that I described before. So how to construct bundle automorphisms from, well, for the analytic torsion scenario, we can take the Hodge star defined by a metric G of t, G of tau, and compose it with the inverse at metric G0. This will give us a bundle automorphism. And similarly, given a family of vector fields x tau, one can find a bundle morphism covering the identity such that x of tau is obtained by x of 0 by application of this morphism, and then the contraction with x of tau on k forms is related to the contraction along x of 0 by the adjoint map from t star to t star. So then we obtain, as a corollary of the previous result, that the superdeterminant of the Laplacian at time tau restricted to the gauge fixing Lagrangian given by the image of the star is independent of tau. And this implies, well, this is the same result that Ray and Singer proved. And analogously, with some additional technical requirement here, which are important, we get a similar statement for the Lie derivative along a vector field x of tau restricted to the gauge fixing Lagrange. So this tells us that both the analytic torsion and the Ruelle, the value at 0 of the Ruelle zeta function are locally constant functions of the gauge fixing parameter. Notice that here we are sort of bypassing the interpretation in terms of partition function altogether, right? So that was just a motivation that allows us to use the techniques or find a construction that is reminiscent of finite dimensional field theoretic scenario. But truly what we're looking at here is a bunch of superdeterminant, regularized superdeterminant of operators. Here, there is another type of, sorry about that. This should be the flat superdeterminant. We can put the flat superdeterminant of the Laplacian here as well, because it will coincide with the zeta function regularization. Okay. Before that, so clearly the advantage that we have is that now these two local constancy statements, they are embedded within a larger setup that might enable us to find a homotopy between the image of iota x of tau and the image of d star nabla of tau. And if we are able to do that and satisfy the analytical properties that I required at the beginning, then we would have that the well, the two quantities are the same. So I will give a chromalogical interpretation now briefly. So suggestively, one can compare the following expressions, right? So the Laplacian, which is the bracket of the de Rham differential with this Lorentz gauge fixing operator, can be seen as the square of d nabla plus the codifferential. And entirely analogously, the Lie derivative has the same exact property. So the way we like to think about this is that choosing d star or choosing iota x is simply a different choice of a chain contraction for the de Rham complex. Now, again, in finite dimensions, the torsion of a complex is an invariant. It doesn't depend on the choice of chain contraction. Here in infinite dimension is not always the case, or not necessarily the case, but the interpretation still remains. So heuristically, one can think of the chain contraction in the case of Lorentz gauge as the composition of the codifferential with the inverse, in some sense, of the Laplacian. And for the Ruelle zeta function, we get a similar statement. The condition of non-degeneracy of Lx is not exactly the same, but it is akin and it is related to the non-degeneracy of the Laplacian, which is, for example, related to acyclicity of the complex. But it also is related to zero being in the resolvent set, which is this technical condition that I mentioned before. Zero is not the Polycott-Ruelle resonance of Lx. Okay, so here we're getting a bit technical, but if any of you in the audience has heard this before, maybe can connect. I want to also give another concrete example of how one might think of using this idea of Lagrangian homotopies in a more geometric sense. So if x of g is the geodesic vector field for a given metric g on the sphere bundle defined by g, given any other reference metric g0, which we fix, we can map the geodesic vector field to this reference sphere bundle given by SG0 of sigma. Now, if we denote by R minus sign the space of negative sectional curvature metrics, we have a map that to each negative sectional curvature metric gives us a Anosov vector field inside this space of vector fields on the reference sphere bundle. So the idea here is that if you have a curve in the space of negative sectional curvature metrics, this will give you a curve in the space of annus of vector fields. And precomposing that with the Ruelle zeta function and the analytic torsion, we get two locally constant functions on the space of negative sectional curvature metrics, which coincide, by the result of Fried, at hyperbolic metrics. So, for example, this is already enough to tell us that if we're working on surfaces, given that the space of negative sectional curvature is contractible in that case, well, then you have two locally constant functions on the whole set, and they coincide at the point, so they are the same. The problem in general, though, is that negative sectional curvature metrics are not a connected space in general. So the conjecture by this argument is only extended to islands of annus of vector fields. So the image of this map will give us islands inside the space of annus of vector fields for which you have a local constancy statement. So this can anyway be used, I think, to say, well, if I have a finite number of connected components, then I just need to check a finite number of cases. Finally, I want to give another hint at why field theory can be useful when dealing with these topics in dynamical systems. There is a possibility that one can perturb the BF theory that I defined before by a quadratic functional. And we perturb it at order h bar for technical reasons. Despite this perturbation, we can again treat S tilde as a free action. It's quadratic. This, for example, if we are thinking about Costello's perturbative quantization scheme, this is allowed. And adapting his scheme to a scenario where operators are not necessarily elliptic, you get the following statement. You get the partition function for the twisted BF theory with this extension by this slightly non-local term gives you precisely the Ruelle zeta function at any value of h bar. So here h bar doesn't need to be a formal parameter, actually. It can be any complex number. And we get that we can, in fact, interpret the full meromorphic object as a field-theoretic quantity. There is an alternative here if you want to play around with this, these constructions. When you add a term like this, you can decide to either compute the free partition function, or you can decide to treat this as a perturbation, or even treat it as a functional. So you want to compute the expectation value of e to the f in the background given by free BF theory. Well, if you do that with a little bit of work, applying again the perturbative quantization scheme by Costello, adapted to the non-elliptic scenario by means of these microlocal techniques, you get this statement. I conclude by an outline of possible directions going forward.
May I ask a question?
Yes, of course.
Yes, in the previous page, are we only dealing with the abelian gauge theory, or are we assuming any gauge group?
This is abelian.
Oh, okay, I see.
It's abelian, meaning that there is a gauge group because, but it's abelian. It's a reductive So you change A by an exact form, and that doesn't change your action, A and B.
I see. Is there any possibility of extending this formalism to non-abelian gauge theories like SU2 or SU3?
What formalism? I mean, BF theory in the non-abelian case is well studied, and so you can certainly do many things there. I have not computed or tried to work with non-abelian BF theory in this particular gauge, so that has not been done.
Okay, thank you.
Okay, so as I mentioned, the most pressing point now is to find a direct homotopy between the image of the gauge fixing operator by X and the one obtained by choosing a metric. This, I am slightly afraid, will touch on the to me, completely mysterious topic of hyperliptic Laplacians. I'm not an analyst, so I see it coming, but I believe that this is a very interesting scenario, and it will probably require some sophisticated analysis to make sense of, well, the regularity requirements that I mentioned before. So if any of you is interested and knows something about this, please hit me up, because I think that's the way to go. But anyway, another interesting approach is that of discretizing everything. So in particular, discretizing the dynamical system side of things, and compare it with the discretized version of BF theory, which, for example, was studied extensively by Catanium, Nevrashetikin in these terms. There, the advantage is that everything is finite dimensional, and there is a theorem, and so one can try to, well, claim and prove a sort of version of Fritz's conjecture. Also, perhaps slightly orthogonal direction here is that the BV Laplacian in finite dimensions is tightly related to the Ram differential through an operation called odd Fourier transform. So my question is whether one can use similar microlocal techniques, microlocal analytic techniques, to regularize the odd Fourier transform, so that you take the Ram differential, you apply the regularized odd Fourier transform, and you get some regularized BV Laplacian that you can readily use. So that's just an idea. I think it would be interesting as well to try to extract new topological invariants from BF theory using this contact gauge fixing, and see whether these have any relevance at all in dynamical systems. You see, the useful, well, one of the many useful things of field theory is that it allows you to predict certain results by means of heuristic manipulations. So perhaps one can try to play around with this stuff and come up with interesting conjectures that someday someone will prove. And yeah. Another possible extension of this research project is to include boundaries into the game. So as I said, I always assumed that the manifold was compact without boundary, but there is a lot of work in dealing with higher codimension strata in the BV field-theoretic world. And so I wonder whether the results in that direction would be interesting as well for applications in dynamical systems. And finally, I mentioned the extension to non-acyclic cases as well. There was work by Viet Tang and collaborators recently where they extended Fried's conjecture to what they call dynamical torsion, derived torsion, by essentially allowing one to change the representation rho and allowing for zero mode, so non-trivial kernel for the Lie derivative operator. And with this, I'm done.
Thank you, Michele. All right. There were already some questions during the talk, but please don't hesitate to ask more. You can just unmute yourself and go ahead if you have questions.
Could you explain why the BF theory is called BF theory?
Yes.
And what is its relevance?
Okay, so where did I put it? Well, the reason why it's called BF theory is not very exciting. So as you can see here, you can think of dA as the curvature of A, which is typically denoted by F. And so this is called BF because you can write it as B wedge F. In the non-abelian case,
where B is what? I mean, is B the magnetic induction or?
No, the B is just
No.
some D-2 form on your manifold, and A is just a connection on some principal bundle. So it's very general. Now you can write several theories as perturbations of BF theory. So you can write general relativity. General relativity in 3 dimensions can be written as BF theory. You can write Yang-Mills theory as a perturbation of BF theory. You can write general relativity in 4 dimensions and as a perturbation of BF theory. So there are a number of examples of relevance that stem.
Yeah. So is BF theory linear? I mean, the action looks quadratic. Is it correct?
Yes. Yes, it is quadratic. It has it's first order, but it is quadratic.
So the differential is the differential operator is first order.
Yes,
so
it's
you
the
don't
Derham,
have...
it's the Derham operator.
Okay, and both B and A are commuting. I mean, these are bosonic.
Correct. Yes.
Okay.
And we are not yet considering the external matter fields in terms of like quantum electrodynamics.
Nope, not at all. This is a topological theory. So here the point is we're not studying BF theory in all its possible declinations. Here we're just saying BF theory can be used to connect with dynamical systems in this way. It was already known since Schwartz that BF theory can be used to compute the partition function, the analytic torsion. So it has pretty much a meaning in terms of the topology of the underlying manifold. So it is a tool to construct topological invariants, very much like Chern-Simons theory, which is a cousin of BF theory. Another, if you're interested, another relevance for BF theory is that it is thought to be the effective theory for topological insulators. I know maybe some of you are experts here, but let me say it anyway. Topological insulators can be related, let me put it in this way, with BF theory, much like quantum Hall systems are related to Chern-Simons theory.
And what is the gauge invariance of the BF theory?
I mean, for me, gauge invariance should be the statement that, okay, I see. From a physical point of view, if you think that these theories will produce something physical when you extract their observables, their gauge invariant quantities, then it's a bit hard to imagine that the quantities that you extract will depend on the way that you extract them. But so far for field theory, this is, well, a theorem sometimes. I think the interpretation here is really that this theory, much like Chern-Simons theory, is a way to extract topological information. So if gauge fixing is done by means of non-topological data, such like a metric, then the information that you extract has to be locally constant on a family of choices that you can make. So the statement, I think, to answer your question is gauge fixing invariance is the statement that BF theory is about the topology of the manifold. Does it make sense?
Well, as you said, it is not just about topology. I mean, you said that if you have a family depending of something depending on a parameter, then this is constant. So, so you have to choose.
Yeah, I mean, to define analytic torsion, you also have to choose, but then the choice is immaterial. So here, the idea is the same. You need to choose something, but that choice is immaterial.
Okay. Any more questions, discussion points? Okay, maybe let me ask one question I was saving for the end. So when you talked about perspectives for future research, there was the one about maybe regularizing the Laplacian for quantum field theory.
Yes.
So yeah, in my experience, well, that is always then facing some renormalization.
Right.
So do you have some ideas how this could potentially work, and like what sort of renormalization approach would that be compatible with?
I mean, to be honest, I have tried to embed this in some perturbative algebraic quantum field theory setting, but I have failed mostly because of ignorance. I think it is possible that that this can be phrased in those terms by all means. Now, yeah, I mean, different renormalization schemes might work. I mean, Costello has his own approach, which in order to apply to this case, we had to tweak a little bit because he's only working with elliptic operators.
Right.
As far as I know, at least in his book. And so here, for example, that that approach doesn't immediately work because the Lie derivative is a nasty operator from that point of view. So there you really need some microlocal shenanigans, let's say. I know that your community is closer to the microlocal analysis.
Microlocal, yeah, that sounds good.
And so I can see this working in some way.
Oh, Okay, now that's an interesting thing to look
I
at.
don't know if it makes sense to apply Epstein-Glaser to this setup, but maybe.
Yeah, it don't know either, but yeah, that looks like interesting thing to explore further. All right, any more questions? That does not seem to be the case. So let's close for now and thank Michele again.
Thank you very much.